So good morning, everyone. Hope everyone has had a chance to read the announcements. Quiz 2 is tomorrow. Students have access from 8 a.m. to 12 midnight. Well, actually 11:59 p.m., a minute short of midnight. Time length for the quiz is 20 minutes. It is not going to be live and proctored. Live in the sense I will not be on Zoom, so students are not required to be in Zoom. So in that sense, it is an offline quiz, but it's on Pearson, so it's online. So hybrid, if you wish to call it that. But does that make sense? Right? Exactly the same thing that we've been doing for quiz 0 and quiz 1, except it's not going to be proctored. Okay. Time length is 20 minutes. It'll be based on the Zener diodes and analysis. We'll cover the last problem example today. And then let's see. Canvas submission also opens and ends at the same time, 8 a.m. to 11:59 p.m. So again, keep that in mind. I mean, if someone starts at 11:35 or 11:40 p.m. at night, both will close at 11:59. Okay, so give yourself sufficient time to get everything done. Okay, and again, as usual, if you have any questions, reach out to me. Okay, so for now, let's continue with Zener diodes in the example problem for analysis. So we were a bit rushed for time at the end of this example. If you have reviewed this and have any questions, please ask. Anyone? Okay, so then let's go into the example for Zener regulator with load. Okay, for Zener regulator with load, we have this example problem with a Zener diode. Actually, let me change. One Zener diode, a supply voltage. To write down supply voltage. This is the series resistance. We use it to limit the current that flows or control the current that flows in a circuit. And this is the load RL. RL is simply noted as a load resistance, but in real life, that RL load could be any large circuit or device. For instance, if you plug in your laptop adapters, your laptop chargers into the laptop, your entire laptop could be RL. Okay. RL is the Thevenin equivalent resistance of a larger circuit. Okay. This is how we would analyze this. So VSS is the supply voltage. R is the current limiting resistance in series. RL is any load. And basically, it is the Thevenin equivalent resistance of a larger circuit. Essentially, whenever we perform any kind of circuit analysis, we always want to reduce the system down to as simple as possible, meaning combine all the components in the circuit that are possible. If you have multiple capacitors, you want to combine all the capacitors in one. If you have multiple resistors, you combine all the resistors into one, and so on and so forth. Yes. Depends on what you're analyzing. So question being asked is about circuit blueprints. More often than not, non-EE majors would not be asked to do something like this, but a real life case would be where there is a system, perhaps there's a machine that is running, it has a small power supply, it blows out. You call tech support, they can't get to it for maybe a few days. Maybe if it's critical, they can't get to it for a few hours, and you need to get it up and running. So even if you're a non-EE major, you're part of a team, you're working in there, maybe you have an EE major in there to work on it. But if you're a non-EE major and you are the one person who's responsible for it, it'll be up to you to figure out where the problem is. Okay. Sometimes that might be easy, sometimes it might be difficult. But again, you would have to be aware of what that system is and what it is doing and how the circuit is actually, working in that. Any kind of electronic machine or electric machine will have some sort of power supply, right? Some sort of power supply system at the front end. Anytime a system goes completely dead, 90% of the time, it's always in the power supply line. So even if a small Zener diode like this blows out, then the rest of the system is, redundant. Think of it this way. It's like a vehicle runs on a lot of different components. We would say the engine is the biggest, the most important one. But if you lose your keys, it doesn't matter. Nothing will work. Especially in modern vehicles, there's no way to just hotwire a car, right? So a tiny component can render everything useless. Anyway, let's come back to our example problem. So we have here a regulator circuit with load. Regulate simply means you're controlling. You're controlling a system. And in this case, what the Zener diode is doing is it is controlling the output voltage from the supply, the output voltage from the supply going into RL. Okay, going to RL. So regulator controls the voltage, the supply voltage that goes into the load. And this is how you obtain a constant flat line. Remember, in the previous slides, I pointed out before we started Zener diodes that the output of a power supply is not often the voltage that we need, right? We apply a slightly higher voltage and then we regulate it down to our requirements. So Zener diodes are used to do that. One word also about analysis. All of the analyses that you're performing in this chapter and going forward in 321, they all come from 201. There's nothing new about these analysis techniques, okay? So there was a student comment saying that we haven't seen these circuits before, neither in the class examples nor on the homework, and so this is maybe a bit unfair. So I would like to point out, well, two things. In real life, you will always see something new every day at work, right? So it'd be up to you as an engineer to put things together. Second thing is all of the circuit analysis remains the same from 201. The only thing that has changed are the components we are using, meaning the diodes in this case, then the transistors going forward. So we had diode circuits in the in the first half of this chapter, p-n junction diode. Now we have Zener diodes. The analysis we perform, these equations that we use, they're still exactly the same. The only thing we need to do is we remove the nonlinear component from the circuit and we analyze the rest of the circuit without it. So when we remove this nonlinear component, what are we left with? If you look at it like this, we are left with a linear circuit with a power supply and a few resistors in the circuit. The only nonlinear component is your Zener diode, and we brought it outside. Okay. So even though it seems like you haven't seen the circuit before, I would like to assure you that you have. You have seen this circuit before in 201, especially chapters 1 and 2, resistive circuit analysis. Okay. That's where the analysis techniques come from. The equations are also all the same. No difference in the equations that we use. Right? So we brought Zener diode to the outside. They are in parallel, so it doesn't really matter how we draw out the circuit. Electrically speaking, that's exactly the same thing. So we brought all the linear components inside. Now our linear circuit looks like this. And instead of the battery, I'm going to draw out this symbol for the power supply. And this is where I'm going to analyze the rest of the circuit without my Zener diode. Okay, RL is inside, this is R, and this is VSS. So we analyze the rest of the circuit without the diode, and we need to know what the voltage is that is being applied at the output terminals. And for that, we go back at the end of chapter 2 and 201 to determine the Thevenin equivalent network. So you determine the Thevenin equivalent network or equivalent circuit. Also, circuit and network in this instance, or in 201 and 321, are kind of synonyms of each other. We typically refer to a circuit as a network or a network as a circuit. In this case, it's both the same. So now this is relatively straightforward. You have one voltage source, two resistors. We find the Thevenin resistance and we find the Thevenin voltage, and that would give us a Thevenin equivalent network. So if we do this, I can reduce it to figure number C, which is right here. VSS, R and RL gives me VT, the Thevenin voltage, and R and RL combined give me RT. As a quick refresh, if I'm analyzing this circuit in figure 3, to determine RT, the Thevenin voltage, I would replace the power supply with a short circuit because it's a voltage source, and I would find RT at these terminals. And RT, looking back into the circuit, comes out to be R in parallel with RL. So this would become R times RL divided by R plus RL. So let's take a 10-second pause, perhaps a longer pause, and let me know if you have any questions. Okay. Then let's go to Thevenin voltage, which is VT. And for Thevenin voltage, we go back to our original circuit. We have VSS, R, RL. Is that something of mine? Okay. And then we find VT at the output terminals. So this is RL, this is R, VSS. When you have one voltage source and you have two resistors, these resistors are in series, even though it doesn't seem like it, because there is no component connected at this node. So I could redraw this circuit as a voltage source, resistor R, resistor RL, and I'm simply measuring or taking the output at this point, which is VT. And you have resistors in series, a fraction of that voltage appears across each resistance. So in this case, voltage across RL would be a fraction of VSS, and the fraction is given by the ratio of RL to REQ, meaning RL divided by R plus RL. Okay. So I want students to understand the setup and the analysis before we plug in the values and do the calculations. Okay. So far, again, we have a Zener diode in there. We are trying to determine what the voltage regulator circuit is. I have not presented the values or anything, but I just wanted to show students, no matter what the system is, you would analyze this by removing the non-linear element and then analyzing the rest of the circuit as a linear circuit analysis. Okay. So right now, Zener diode is out. We are not concerned with that right now. We are simply looking at the rest of the circuit. So does that approach make sense so far? Okay. So now, once you have the Thevenin equivalent network, let's go back to the top. What is it that we are trying to do? We have a Zener diode. We want to use it as a regulator. Regulator means we control the voltage coming from the supply and going into our load. We want the load to receive a constant voltage, right? So in that case, if you think backwards, it means that no matter what the voltage coming from the supply is, let's say our requirement is 5 volts. If the load is sending, if the supply is sending in like 7 volts or 10 volts, 15 volts, 50 volts, the Zener diode should send 5 volts to your load. Make sense? Now, as voltage increases, what happens? Ohm's law, V equals IR. So as voltage increases, R is constant because RL and R are not going to change. What happens to current? Right? So voltage increases, the total current in the system increases. Where is that total current going? If you look at the circuit, voltage regulator circuit right here in A, this current is coming through here, right? That is IS, supply current. It reaches the top node, splits in two. Let's call this IRL or just IL for that matter. Let's see, we have no inductors here, so we can refer to that as IL. And this one's coming down here. Let's call it IZ. If RL doesn't change, R doesn't change, but the VSS changes and VL or VZ remains constant, then the current IS has to change. Just simple physics. Current I changes. Now, RL is not changing and VL, the output voltage, is also not changing. So where is that extra current going? KCL equation. IS is equal to IZ plus IL. Voltage regulation, or simply regulation, means you're keeping something constant. In this case, that means your VZ, or VL for that matter, is constant. If VL is constant and RL is constant, then IL is also constant, right? That current also has to remain the same. So looking at that KCL equation, what is the quantity that has to change? right? We have the KCL equation, IS is equal to IZ plus IL. If IS increases, but IL remains the same, then IZ must increase. And this is the key point. This is the key point. In regulation, Zener regulation, VZ remains constant. But IZ must change. IZ must change. And when IZ changes, what is the equation for power? Power is simply the product of the voltage and current applied to a Zener diode. That means PZ, power for a Zener diode, is the voltage for that Zener diode times the current for that Zener diode. So if IZ changes, then there is a upper limit for the operation of a Zener diode, and that is given as PZ max. Yes, go ahead. Oh, sure. The circuits or no, so they are in, so for our analysis purposes, it's the same circuit. In real life, RL is something else. RL could be your laptop, could be your smartphone, could be anything. IL has to remain constant because, well, it's the load. So a load requires a standard voltage and standard current. But VL also remains constant. VL would be the same thing as VZ in this case. VL, because they're in parallel. Yeah. All right. 10-second pause. Any questions? Don't get bogged down into the equations right now. Understand the qualitative explanation first, then you can review the quantitative equations. So does that make sense? The steps that I've outlined so far? Okay. So let me summarize in brief. We have a supply voltage. Supply voltage is connected to a load. We want to, of course, control the current, the total current coming from the supply. So we have a series resistance in there, which is R. That's always true. Okay, we always have a series resistor. We always want to control the current, without which R is equal to 0, current goes to infinite, right? So current limiting. And then we have a Zener diode connected in parallel to the output load. So if VSS goes above a certain limit, meaning let's say the system VL required is 5 volts, you would connect a 5 volt Zener diode in parallel to that load. If you connect a 5 volt Zener, no matter what your supply voltage is, the Zener diode would hold 5 volts across it. So only 5 volts goes to the load. The analysis portion comes about the extra current. What do we do with the extra current? Meaning the voltage across the load remains the same. RL doesn't change, VL doesn't change. So IL has to remain the same. If IL remains the same, but VSS increases, that means there is extra current coming from the power supply. That extra current has to go through the Zener diode. So if it goes through the Zener diode, the heat energy is being transferred, which creates a lot of heat. that Zener diode has to be manufactured to handle and dissipate all of that thermal energy. And that's where the maximum power rating for a Zener diode comes from. And that is the crucial factor in designing or in analyzing regulator circuits. Okay, that's the recap. So now let's look at the problem. So we have VSS given to us. So these are given values to us. VSS is given to us as 24 volts. Okay. R is given to us as 1.2 kilo ohms. RL is given as 6 kilo ohms. So Thevenin resistance of the load is 6 kilo ohms. So first question being asked is, what is the output voltage, VL, and what is the total supply current coming from the source? Okay. Excuse me. Let's see. VL. So if you want to determine the values, actually not. VL is, okay, VL we'll assume later. So if you want to determine the equations, we can use the load line analysis technique. So that's on the next page. And I'll come back to here after we get our values. We can write a KVL around the loop. If you write KVL around the loop, we have VT plus IDRT plus the diode voltage drop equal to 0. Right? The Thevenin equivalent circuit reduces R and RL to one single resistance. VSS is now VT. So if you apply KVL to that Thevenin circuit shown in figure C, let me note it here, KVL in figure C, then the supply voltage VT plus TRD plus VD is equal to 0. We can find the operating point by plugging in VD as 0 and ID as 0, and we can plot it on the load line. If ID is 0, then VD is equal to VT. And if VD is 0, then ID is equal to VT minus RT. So here, if I have my VTH, let's see, this is 24 volts. This would be 24 times RL, which is 6,000, and R plus RL, 1200 plus 6,000. So my Thevenin voltage would be 7,200, 612, 24, 20 volts. 20 volts. And then this would become minus 20. And let's see, VT is, yeah, VT is minus VT, so minus 20. And this would become minus 20 milliamps. Minus 20 divided by, that's my RT. Oh, RT is R times RL, so it's 1,000 ohms. 1,200 times 6,000 divided by 7,200, that would give you 1 kilo ohm, 1,000. All right, any questions? Okay, so we have that. We can plot that on the load line. But what happens? We now need to find out the range of supply that this system can handle, right? We just said there's an upper limit. Upper limit means the supply voltage cannot exceed that point. If you look at your, as a real life example, if you look at your any kind of charger, smartphone charger, laptop charger, it'll have a voltage rating. Okay, that voltage rating previously, just until a few years ago, would be either 110 to 120 volts, or if you're abroad, it would be about 200 to 220 volts. With modern advances, now your input voltages are 100 volts to 240 volts, meaning you can use this anywhere in the world without needing a modification. But the circuit analysis portion of this would mean you need at least 100 volts for it to work, and you cannot apply a voltage more than 240 volts. That's what it means. So there is a range of values that you can apply as input to any one of your chargers. Okay, if you exceed that, it's going to blow it out. If it's going to be lower than the 100 volts, it's not even going to work. So in the Zener diode system, we have to find both the minimum as well as the maximum. That's what we're going to do. We are going to find the range of values of the power supply voltage that the system can operate safely. Lower is easier. Okay, lower is easier. Let's say, for example, in this particular instance, let's use the example of VZ as 10 volts, right? Let's say you want your VL to be 10 volts. That means your VZ has to be 10 volts. Okay, if your load requires 10 volts, then your VZ, Zener diode, must supply 10 volts. You have to have a 10 volt Zener diode. So now, what is the minimum voltage that is required to turn this on? If it was directly connected, you have a supply, you have a Zener diode, and you have RL. What is the minimum voltage required? 10 volts, or just slightly above 10. Make sense, right? But we have a current limiting resistor in series. So we have to account for the fact that when current flows to the system, that resistor R is going to drop some voltage across it. So we have to add that to your V in. We have to add that to the 10 volts so that V in has to operate at that voltage. So it has to be slightly higher than that. Otherwise, the Zener diode is not going to turn on. If you apply 5 volts, Zener diode is not turning on, just 5 volts would appear at the output. That's it. Nothing else would happen. So let's find the minimum voltage. What would be the minimum voltage? Well, that can easily be given by KVL. So VSS minimum would be VZ plus VR. And VR in this case is the voltage drop across this resistor. Okay, this is VR. Voltage drop across that resistor R. Because again, remember, it's a series circuit in that sense. Current flows through R, causes a voltage drop, then it goes through VZ, and then anything else is sent to IL or VL. So let's draw the circuit here on the side. you have VSS, you have VR, you have diode voltage drop. Oh, went a little bit longer. And then you have RL connected at the output. Current flows in this direction. And this is VL or VZ, whichever one you want to call it. If you apply KVL, you have VSS is equal to VR plus VL. So we can find that voltage by applying voltage division, VL or VZ. Again, I'll point out VL is equal to VZ. Okay, so if you use VZ, it's the same. If you use VL, it's the same. So VL in this case would be your VSS minimum value times your load resistance divided by R plus RL. Voltage division. Again, you want the voltage across RL, so it's RL divided by R plus RL. Therefore, if I want to find VSS minimum, it would be VL times R plus RL divided by RL. You plug in the values and you would obtain an answer of 12 volts. 12 volts. Let's take a pause while you write it down. Let me know if you have any questions. Yes. Okay, so one question is, did we replace VZ with VL? There is no replacement. It's exactly the same voltage because they are in parallel. So VZ and RL are in parallel. So we can either use VZ or VL. Sometimes I like to use the terms interchangeably, but I always try to point it out to students because, students should be familiar with both. Yes. And the second question? So a question being asked is, if circuits get more complex, is there another method to calculate? The answer would be that depends on the circuit. So we always reduce it as much as possible. And if we think back to the beginning of 321, I stated that most of the techniques that we use for 201 are analytical, meaning we have a fixed equation. The systems don't change much. So if you plug in an equation, that's the answer you get. For nonlinear elements like diodes and transistors and FETs, the methods are numerical, meaning we don't always know the answer. We have to create a lot of models, and there's an iterative process where we would try an equation, obtain an answer, see if that answer matches up with what we require. If not, we go back, refine the process, and we rinse and repeat constantly. So the answer is, there is no single way to actually, just predict what is going to be the most efficient method. We have to keep on iterating and then determine what's the best way. Always keep in mind, the circuit analysis techniques are still the same. They don't change. Okay. Oftentimes, when we have circuits, and we will see that a little bit in 321, but not a lot, we have multiple models, meaning for the diode, single diode, we saw like 2 or 3 different techniques, right? Where we use ideal diode model. There is a offset diode model. There is also a small signal linear analysis model. There is a diode equation that we looked at. All of those will work in one particular scenario, but it will not work for all. Okay, so if you want to do a quick and easy analysis, we'd use a ideal diode model. Then you perhaps move to offset diode model. So again, the answer is you will see new circuits all the time. The approach remains the same. You simplify it as much as possible, and then you logically think about which equations would fit. There are only 3 equations. If you just took the class 201 with me, then you know what I'm talking about. But as a reminder, I will tell all students 201, it seems like you learned a lot of analysis techniques, but there are only 3 equations in the entire course. Ohm's law, KCL, and KVL. That's it. All other techniques are based off of these 3 analysis techniques. Okay, Ohm's law, KCL, and KVL. Node voltage analysis, mesh current analysis, superposition, they are all based on these 3 equations. So it's the same 3 equations you keep applying in any order that you wish. As an example, we look at the current analysis technique. What did we do here? We applied KCL at the top. We applied KVL here, right? Then there's the power equation, of course, P is equal to VI. So those are the same techniques that you'll use no matter the circuit. It is up to you as an engineer to think and apply those equations. All right, any other questions? Okay, so let's look at the answer. The answer is what? 12 volts, which logically makes sense. It's higher than 10, but not a whole lot higher, because you have a resistor to limit the current, which is about 1200 ohms. If you have a current limiting resistor, let's say higher than your RL value, 10,000 ohms, your RL itself is only 6,000, but your current limiting resistance is 10,000, meaning a lot of the voltage would be dropped or eaten up by that resistor R. And then this value, VSS minimum, would be higher than 20 volts. So that's another logical reason. So anyway, we found the minimum value. Let's find the maximum. So for maximum, let's do this. We'll have to make an assumption, right? And this can go either ways, right? You have a system. That system might require certain amount of voltage and certain amount of current, or you might have certain components at your disposal. Let's say a Zener diode with a 0.5 watt rating, 1 watt rating, 2 watt rating, so on and so forth. So if you are limited to certain components, then how can you design your system based off of those components? So let's look at that scenario. Let's say we have a Zener diode, for instance, with a maximum power rating of 1 watt. Okay, maximum power rating of 1 watt. That's the Zener diode we have available at our disposal. So if maximum PZ is 1 watt and our load requires 10 volts, that means our VZ, Zener diode voltage, also has to be 10 volts. So this means my VZ has to be 10 volts. And it also means there is an upper limit for the Zener current that can handle, right? If PZ max is 1 watt and VZ is 10 volts, then IL max cannot be more than 1 over 10. P is equal to IV, or P is equal to VI. So I is P over V. So 0.1 amp or 100 milliamps. 100 milliamps. Which, by the way, is a huge amount of current, just generally speaking. And then, if that's the case, we can now calculate what IL, oh, sorry, this would be IZ max, not IL max. This would be IZ max, Zener diode max. So from here, I can calculate IL. IL, I can use either the KCL if I had those values, but an easier way is to simply apply Ohm's law. V equals IR, so I is V over R. That gives me 10 over 6,000, which is 1.667 milliamps. Okay, so I have IZ max, I have IL, which in this case, if VL is going to be fixed at 10 volts, then this also means that this is the maximum value of IL max. So the total current coming from the power supply, IS total, cannot exceed IZ max plus IL. So it's not point, it's 100 milliamps plus 1.667. And so this comes out to be 101.667 milliamps. So my total IS from the supply cannot exceed this value. Let's put this down in IS cannot exceed that. If it exceeds it, then your Zener diode will blow out. So then let's figure out the maximum voltage drop across that load resistor. We established that my supply voltage, minimum supply voltage to turn on is 12 volts. Maximum current through that circuit coming from the source cannot exceed this value. So what is the minimum power rating or the minimum value of the voltage that is dropped across? Well, we can, excuse me, we can calculate that by finding VR and adding it to VZ. Okay. We determine the maximum current that can come from the supply. That current from the supply also flows through VR. Remember, this is IS. IS is going through here. So if maximum value of IS was 101 milliamps or 100 milliamps, what is the voltage across VR? That's the max value, right? That's the max value. It cannot exceed that value. So VR, and again, Ohm's law, right? Same circuit analysis techniques. Ohm's law, VR is your maximum current, which is 101.667 milliamps, times your R, or sorry, times the voltage, 12 volts, and that gives me 122. 122. And therefore, max actually, let's just wait while you write it down. Let me know if you have any questions. And then we'll take a break. Yes. The 12 is from here. The minimum voltage that is required to turn on the Zener diode. So this would be kind of like the worst case scenario. You have the minimum voltage, but the maximum current. Okay. This is the minimum voltage required to turn on the Zener diode. Without that, the Zener diode is not going to turn on. The Zener diode is rated for 10 volts. If you just apply 10 volts, then the resistor R is going to drop some voltage across it. Your Zener diode voltage would be less than 10 volts, so it would never turn on. Your load would only get like 8 volts or 8.5 volts. Remember, Zener diode works in reverse bias. It has to have a minimum voltage for it to turn on. It has to go to breakdown. If it doesn't exceed that minimum voltage, then the Zener diode remains off. It's in reverse bias. If it remains off, it may as well not be part of the circuit at all. Okay. I know it requires a lot of review and reading of this concept before it will start to make sense. So I encourage you to review it and then ask me as many questions as you want. Yes. Max voltage across the load resistor. Yes, that's what we're trying to solve. That is what we're trying to solve for. So this is, so first we established from our Zener diode power rating, what is the maximum current that can come from the source? So Zener diode power rating was 1 watt. Then we determined, from there, we determined what the current for the load is. The current for the load came out to be 100 milliamps. Then we added it right here. Oh, sorry, not the load. From Zener diode power rating, we calculate the maximum current that the Zener diode can handle, which is 100 milliamps. We already know what IL can be, which is 1.667. Okay. So Zener diode can handle max of 100 milliamps. Your load requires max of 1.67 milliamps. You add those together, your supply voltage cannot exceed that total. If it does, then your Zener diode is going to blow up. Yes. No. So that is basically, so this value of this voltage combined with this max current represents kind of like the worst case scenario on one end. So you have the minimum voltage that is required to turn it on, but the maximum current that is coming from the Zener, from the supply. Wait. Oh, I see what you're saying. Oh, so that would be 1200. Yeah, I'll change that. You had the same question? Okay, yeah. So that would be 1200. 1.2 times 100. Yeah. So let's see. 10 raised to minus 3. That gives you 1.2. 1.2 times 101. That gives you 122. Yeah. Missing 2 zeros. Good catch. See, that at least lets me know that students are following. Does everyone see the error? Okay. So maximum power rating for the Zener, 1 watt. That gives us the maximum current the Zener can handle. We add that to the load requirement. That's the maximum current that can come from the power supply. If that's the maximum current coming from the power supply, then we calculate the maximum voltage drop across that load, across the resistance R, and we add that to VZ. That would give us the maximum supply voltage. And so VSS max would be VR plus VZ or VL, that would be 132 volts. That's the maximum voltage you can apply to the system for it to still work in the same range. So the range is 12 volts to turn it on, and maximum is 132 volts. I want a trapezoid. Even worse. All right, I give up. That's not going to work. Anyway, think on the steps, and we work backwards of the power rating of the Zener diode. Make sense? Another view of looking at this is, instead of looking at the power rating, maybe we want to look at, maybe voltage is given, or maybe current is given. Then you can figure out what the maximum power required would be for that Zener. So you have a range of Zener diodes, maybe at 10 volts. One of them might be 0.25 watts, and that'll be half a watt, 1 watt, 2 watts, 3 watts. The higher up you go, the more expensive it gets. So if you have a 2 watt Zener, and you have a 1 watt Zener, and you have a half a watt Zener, then you figure out what your system requirement is, and what is the least expensive option that could fit your system, right? This is the other way, saying that, okay, I have a 1 watt Zener, I worked off it, and I determined that I can apply 101 milliamps to it, 132 milliamps. But if you have a half a watt Zener, you have a 2 watt Zener, and your supply voltage is never going to go above 50 volts, you might as well get away with using the cheaper option. Okay, so the other angle to look at such a problem would be from the voltage or the current. And again, the analysis techniques are still the same. There is nothing new about the analysis techniques. It's how you apply them that is new. Okay. So let's take a break now. It's 11:11. Let's meet back at 11:15. 4 minutes. In the meantime, if somebody's thinking over this and has questions, feel free to ask.